All right, so we're introducing multivariable functions, and so this is the start of the calculus of it. All right, so what it is about multivariable functions is we still want to find a rate of change. How is my function changing with respect to a variable? The biggest thing about it is when I'm doing my derivative, I can only take the change with respect to one variable at a time. Right? My function is changing per one variable's rate of change, which means we can't find the derivative in the same way that we did with the one variable case. What we can find are what are called partial derivatives. All right, and so for the functions we're going to be dealing with, since we have two variables, we're going to have two what are called first order partial derivatives. If I had three variables, I'd have three first order partial derivatives. If I had five variables, I'd have five first order partial derivatives. The reason why is because how we have to find them. Alright, so suppose I have my function f of xy. Alright, so f of x with respect to y is the partial derivative of f of x with respect to x. So the derivative I'm looking at is my rate of change with respect to x. X is the only variable that's changing. Therefore, the other variable, the y variable, is considered fixed or constant, and therefore behaves like a constant and is treated like a constant. Alright, so take the partial derivative with respect to only the x variable, treat the y variable like a constant. Alright, so this is called the first order partial derivative with respect to x. The way it's denoted is delta z over delta x, alright, the limit of my function as x is changing. And so remember, the limit is the definition of the derivative. This is the average rate of change. And the reason why we can only do a partial derivative is because the h value represents a change in x. Right? And so it can only do one change at a time. It can't do a change in x and a change in y. I can only do a change in x at once. I can't do both of them because there's only one x value. All right, and so this would be the delta notation is the rate of change notation. It means my function's changing with respect to x, or the function notation, which I primarily use the function notation, but just be aware of when you're looking in the book does like to use the rate of change, which is again delta. Alright, so the change in z over the change in x, or the rate of change notation. Alright, it's the rate at which the function is changing as we change x, and again, the biggest thing that you're going to have to get used to is we're taking the derivative of x, and we're treating y like a constant. It behaves like a constant, and therefore we treat it like a constant. Alright, it's just some unknown constant. Alright, so find the first order derivative with respect to x. Alright, so I want my change in my function with respect to my change in x. Alright, that's the rate of change notation, then f sub x. Alright, so again, change in my function, 5x cubed with respect to the change in x, minus the change in my 6xy, deltas are a little weird, with respect to x, plus the change in y cubed with respect to the change in x. Alright, so the derivative with respect to x. So I take the derivative, just like with the one variable function, I take the derivative of each part. This part, I just remember I'm taking the derivative with respect to x, meaning the change in x is the part we're looking at. Y behaves like a constant. And so this first function is the change in 5x cubed with respect to x. Well, that is an x function, so I just use my power rule. 15x to the second minus, well, I take the derivative with respect to x, so x is the function part. Y is a constant, 6 is a constant. So 6, remember, 6 is just going to come along. Well, y behaves just like the 6, right, because it's a constant multiplier. It's going to come along. I take the derivative of x. Well, the derivative of x is just 1. So it's 6 times y times 1. All right, then the derivative of y cubed with respect to x, so the derivative of the function, or the y cubed part, with respect to x. Well, y cubed, there are no x parts in it, so that part behaves, the y cubed behaves like a constant. and therefore it zeroes out. There's no change in x. Therefore, there's no change in the y cubed, so the rate of change is 0. That part zeroes out. Alright, and then if I write it without the 0, it's 15x squared minus 6 times y. Alright, and there's the derivative of this function, not of x, with respect to x. F sub x. So that's the derivative of my original function as x is changing. Alright, well now we're going to do the exact same thing with respect to y. Alright, so my same function, f of xy, we're going to find the partial derivative with respect to y. So y is the variable that's changing. Therefore, x is not. It's fixed, or like I said, considered constant. So we take the derivative with respect to only the y variable. Alright, what's happening in terms of the derivative notation is it's the change in y over the change in, or not change in y over the change in x. Oops, can't erase that. I'm going to rewrite it over here. So it is supposed to be the change in z over the change in y. Alright, it's the change in my function with respect to the change in my y variable, f sub y. So make sure you make that correction in your notes. And so again, what's happening here is I can only look at one rate of change, right? The h value represents one change. This time the change is my y change. So my y is changing, x is not, x is the same. The y part that's changing. And therefore, we take the derivative of the y parts, holding the x constant and then treating it like a constant when I take the derivative. Alright, so it's the same function I had before. So I'm going to take the derivative with respect to y. And again, my deltas look a little bit like 2's. Alright, so my derivative of my function with respect to y using the function notation. So I take the derivative of 5x cubed with respect to x. Take the derivative of the 6xy with respect to, I said x, it should be y. Sorry about that, guys. With respect to y, right, taking the derivative with respect to y, and then the derivative of the y cubed with respect to y. Alright, so just like before, I'm taking the derivative of the y variable. X is my constant, and so in this first term, it's 5x cubed. There is no y part. Alright, so there's no change. So this rate of change, no change, is 0. Alright, so that zeroes out. I take the derivative of 6xy with respect to y. Well, 6 is a constant. X is behaving like a constant. It's the derivative of y I'm taking. The derivative of y is 1. So it's 6x times 1. Plus the derivative of y cubed with respect to y. Well, since it's y variable, I can take the derivative of y using my rules. And so that's the power rule 3y squared. And so the derivative with respect to y is a negative 6x plus 3y squared. And so my function's changing differently because the y parts are behaving differently, right? And so my function's changing differently with respect to y. This is how it's changing with respect to y than it did with respect to x, right? With respect to x, it was 15 times x squared minus 6y. That's how it changed. And with respect to y, it's negative 6x plus 3 times y squared. Alright, and so again, it matters which variable I'm looking at because they behave differently because they have different values in my original function. Alright, so now we're just going to do a couple of simple cases and then we'll pick up some more on the next set. So I'm going to do a couple of examples here and then I'm going to finish them out on my next video to kind of keep these videos fairly short. Alright, so here's my function f of xy. There's my multivariable functions. They just have a lot of moving parts. Alright, so the change in my function with respect to the change in x, so f sub x. There we go. F sub x. And so I only look at the parts with x values in it. Alright, so anything that doesn't have an x value is constant and zeroes away. So the 3y is constant and zeroes out. The 12 is a constant and zeroes out. And so it's just the x parts. I take the derivative and I use my rule. So this first one is just the power rule. So it's 0.9x squared minus. Now the mixed derivatives you just kind of have to get used to. The x part's what I'm taking the derivative of. The 5 is a constant. The y is a constant. They're constant multipliers. They come along. The derivative of the x part is just 1. Alright, and I'm not going to write it down this time, but it would be negative 5y times 1. I'm just going to leave off the times 1. Alright, negative 5y. And then the next one is 2x squared. Well, the derivative is just the power rule. 4x and negative 5x. That's negative 5, right? As negative 5 is a constant, it comes along. Derivative of x is 1. And so there's the derivative of this expression with respect to x. My first order derivative with respect to x. Alright, now my first order derivative with respect to y. Alright, so this time the y parts, there's only 2. Alright, I'm going to circle them. Alright, this is an expression with a y in it, and this is the only other expression with a y in it. Everything else is being held constant. Right? There are no y parts, therefore there is no change. Zeros away, zeros away, zeros away, zeros away, and so the only derivatives I take are the negative 5xy and 3y. Alright, negative 5xy, well the negative 5 and the x are constants, they come along. I'm taking the derivative of the y this time, well the derivative of just y is 1, so it would be negative 5x times 1, so I'm just going to leave it negative 5x. And then the last part is the derivative of 3y with respect to y, well the derivative of 3y is just 3. Right? And again, this one's, they're vastly different. A lot more going on in the x direction than there was in the y direction. Alright, we're going to do this last example, and then I'm gonna do some more examples. It's just going to be on my next video. Alright, so I've got my p of xy here. I'm going to take my derivative with respect to x, and then my derivative with respect to y. Alright, so remember, when I'm taking the derivative with respect to x, I only look at the x parts. If it doesn't have an x part, it's constant, and it zeroes away. Alright, so negative 4x squared is going to give me a negative 8x. Remember the mixed derivative, the 4 and the y are the constants. I take the derivative of x, which is 1, so I'm just left with 4y. And then the 1920x is just going to give me 1920, and there's my derivative of that p function with respect to x. Alright, now I take the derivative with respect to y, so I'm going to circle the y parts. Make sure I show that that's a plus. And the mixed. Alright, so those are the 3 pieces. I'm going to take everything else zeros away. It's all constant. There's no y parts, so they zero out. So the first y part is the negative 6y squared, which is a power rule, negative 12y to the first. My mixed derivative, the 4 and the x are constant multipliers. They come along. Derivative of y is just 1. So I'm just going to leave it negative 4x. And then the 1600y, same thing. 1600 is a constant. Derivative of y is 1. Alright, and so there's my derivative with respect to y. Alright, so there's my 2 first order derivatives. I am going to do more examples in the next one. So the next set of notes, the next video will be more examples of this, and they are going to be a little more complex. I'm going to involve some of my other rules, like the chain rule and the power rule. Alright, these are kind of some simple cases, so that's my next set of notes. I'm going to stop that there.